Hello and welcome to another adventure-style video. This time I'll be working through simulating a real robot and attempting to train and learn certain actions in a simulator and then transferring that to reality. But if you have a real programmable robot, why would you ever need a simulator? Programming simple actions like a jump that I worked on here can take an hour or more of R&D as you battle battery life, trial, and error. You often also need to rig something up so that you can safely and easily do that R&D, and overall the process can just be somewhat tedious and painful. The simulators that people use range from everything from like 3D graphs to complex physics and ray tracing capable simulators. When you're trying to model something that's going to be heavily physics-based, like four-legged robots, or even heavily visually based with cameras or maybe LiDAR and other ultrasonic sensors, stuff like that, it starts to make sense to want something fairly advanced and as close to reality as possible. At this point, I've only ever heard of NVIDIA's Omniverse and the sims that you can use within it, but it sounds pretty interesting and along the lines of what I'm after, so that's going to be my first stop. Other than the simulator, we need something that describes the robot to the simulator. Now, I don't know much about simulating robotics at this point, but I have learned fairly quickly that people tend to use URDF files, which stands for Universal Robotic Description Format. There are other types of files, but URDF seems to be the most useful. Unfortunately, for this first quadruped that I have, there are no pre-made URDF files, and I have no idea how to make one. That said, the URDF file that we're looking at right now is part of a robot called Bittle, and it just so happens that one of these showed up on my doorstep. You can buy the Bittle pre-made, or you can put it together, and I opted to put mine together just to learn more about it. For those who are curious, it's a $250 quadruped robot. I'll put a link to it in the description. After installing Omniverse, I'll grab Isaac's Sim from the Exchange tab, wait for that to install, and then launch it from the Library tab. Startup takes a minute, but then we get this sort of blank sim canvas, and I want to bring in the URDF for the Bittle robot. For that, I have the repository here. From what I can understand, I need to place this URDF in its own directory, which I'll just call URDF. The reason for this is inside the actual bittle.urdf file. We can see that it wants to find the meshes by going first backwards a directory. Then it's going to look for the meshes folder, which will contain the objects directory. For that same reason, I'll also create a meshes directory for the obj or object directory. At this point, I honestly have no idea what the heck joint monkey is, but I'll probably figure that out later. Let's go ahead and get this into the sim. Next, we can go to the import. Here we have various options. We could actually place the files inside of Omniverse, or we could load them from anywhere on the PC, and so on. I have these folders on the desktop, so I'll go ahead and just import them there. Following some steps that I found from a tutorial on NVIDIA, we'll uncheck the fix base link since the robot moves around, it's not fixed. And then we can lower the joint drive strength to 1000, and then click import to import the actual robot to the stage. It seems to me that things are paused initially, but if you hover over the sim window, you can actually start the physics simulation by hitting play. But right now, there's really nothing else here, so the robot just falls into the abyss. So the next thing that we can add here is a ground plane. I'll hit stop again and then go create physics and then choose ground plane. Then I can move the ground plane up and down a bit and then hit play. Next, to actually move things around on the Bittle robot, we can go to the Stage tab and search for joints. Then, picking one of the joints, we can head down to Drive, and we can move around the target position, which subsequently will move that joint to that target position and actually move the robot in the simulator. And this is cool, it looks really nice, but I really want to do this via code, not manually like this. Through some poking around, I did find you could go to like Window and Script Editor, and this appears to be a Python editor, but I couldn't really find any great information on how to do this or how to plug into the sim via Python. So returning back to that GitHub where I found the original URDF file for the Bittle robot, it's time to inspect jointmonkey.py. Here I see Isaac Gym as a package, but what is this? I don't see it anywhere on pip. Through an internet search, I do find the following page. I'm not really sure how Isaac Gym relates to Isaac Sim. Who's Isaac? We don't know. All mysteries. So I'll hit join here. It does appear to be instant, at least at the time of my going through this. The download is a tar.gz. I can extract this, and essentially there's a README that points to an HTML file that helps you to get started with everything. Once everything is set up, I can run the jointmonkey.py, which is the one that actually came with the package, and things are starting to make sense now. So the GitHub suggested that we go into the assets directory, create a new directory called meshes, and place objects within there. After doing that, we want to place the Bittle URDF file into the URDF directory. Then we want to replace the jointmonkey.py that came with the examples with the one from this repository. I'll just copy and paste it over and save. Finally, we want to run the jointmonkey and choose asset ID 7. So going back into the Python examples, opening up a terminal and running jointmonkey with ID 7, we can see that we have the Bittle robots articulating their joints. Now, I finally feel like I'm onto something, but these Bittles are just floating there. They're not being impacted in any way by physics, and that's really what I'm after. Checking some of these other examples, I'm fairly confident that 1080 balls of solitude is going to at least have some gravity involved, since in a physics simulator, a ball would be very boring if it didn't have gravity. Sure enough, it does indeed appear that these balls are affected by gravity. Now, when I pull up these two scripts and kind of look through them, I don't see anything here immediately. I know it's here. I'm 100% confident there's something here, but I don't see what it is about this that is different than jointmonkey that is bringing in the physics. So then, of course, the next thing I wonder is, what if we come down to ball.urdf and replace that with bittle.urdf? So let's save that and run that. And yeah, that looks like it worked. I think I'm going to call this the Bittle bomb. So gravity and other physics is definitely working here. I see legs bending and stuff when they hit the ground or run into each other. So this is even more so we are on the right track here. Checking the files again, I notice line 91 in jointmonkey.py where fix baselink is set to true. And that is surely our problem. Changing that to false and running things, I can see that was indeed the issue. After this, I've created a simplified script to just simply load in the robot and do nothing more. There's really nothing special going on here. But after running this, there's some strange sliding going on. I've only set starting positions for the robot here. I'm not actually issuing any further commands, but yet it's just sliding. So then I play with various settings like friction and stuff like that, and I am able to slow the sliding down slightly, but it's still happening, and I'm fairly confident that the settings that I am going with to slow things down will also negatively impact physics down the line. Then I find that if I leave friction high and move the limbs around, essentially to cause drag, I can slow down or even stop the sliding, but I'm unable to determine how to reasonably handle for this, and I know something is still just wrong here. Since it seemed like the sliding was the worst on the balls of the feet, I wanted to see if this was happening in the Isaac sim instead of the gym. Once you've created the scene that you want in the sim, you can save it as this USD file, which is Universal Scene Description, which contains information for everything, including your bot, the lights, ground plane, and other objects, and so on. Since the URDF loads with the Bittle on its joints in a sort of kneeling position rather than the feet, I went ahead and manually adjusted it so it would be on its feet. After doing that, and then running the simulation, Bittle clearly isn't sliding anywhere anymore. I asked the people at NVIDIA who work on Omniverse and Gym why the sliding was happening in Gym, but wasn't hearing anything back, so I started to wonder again about just simply using Isaac Sim instead of Gym, because it didn't appear to be happening there, which was weird because I'm pretty sure I've read that the underlying physics is actually the exact same in Gym and Sim, but I don't think that's true. I mean, just what I'm seeing looks like the physics is much better in the sim. But the problem is I still struggled with finding examples in clear documentation to do even the most basic of things in Isaac Sim. The online available documentation is extensive, but it's not super clear for a newcomer in my opinion, with things like how to just load in a scene or a URDF, or even how to import the Omni package that you see in various examples. That said, I'm very guilty of being a high-speed skimmer and not a very good RTFMer, and I'm sure I'm just simply missing something super obvious here. So I started going back through the documentation and videos and stuff like that. As I was rewatching one of the Isaac Sim videos, I noticed the terminal location of one of the presenters, which was here in a hidden directory. And in here we have our own version of Python, which also has the Omni package. It also has a very juicy looking Python samples directory. Inside of there, it even has a simple directory. Now that is my style. Here, there are exactly what I was looking for, examples of loading a URDF, loading an entire scene, and articulating a simple robot. This is exactly what I needed and what I was looking for. I'm not sure how I missed this. So I started off by loading my Bittle scene. And that's not quite what I was hoping to see. I'm honestly a little confused and heartbroken here, but still very determined to figure this out. Initially, I thought I forgot the joint drive strength set to 100,000 or something like that, but instead I found that even after importing, if I select the joint and head down to the drive section, it's actually set to 10,000, despite setting the drive strength to 1,000 on the import. I'm not actually sure what a joint's drive force is versus its strength. Maybe these are the same, maybe they're different. And I don't even see a strength setting here, but I decided to set this to 1,000 for all 8 joints and see if that made a difference. Next, I want to use Python to articulate the joints. So I copy the Franca articulation script, call it Bittle art, and edit it. The first change is to load the Bittle USD instead of the Franca one. Now, I don't quite understand line 41 here. What is this /panda, and what would it be for Bittle? I decided to load the sim manually, find the FrancaBot, and then search the stage for the FrancaBot for panda. It appears to me that panda is just where the joints are located. I don't really know anything about this robot, so I'm just kind of guessing here. I don't know why it's called panda. So then I load the Bittle next and search for my joints, and I see that their paths are in /Bittle. So I presume that this is probably what I want to use here. Coming back to the script, I go ahead and change that run things, and while waiting, I notice that we're almost certainly going to fail because the panda joint 2 is not going to exist here, and we want to use one of our joint names. I'll go with left back shoulder joint and increase these ranges so we have more frames to actually see things happen, and set the target to -1.1. Since I think the max range was something just barely over 1, like -1 to 1 or something like that. So things load in a bit spicy. I think this is just because the robot still moves all legs from that kneeling base starting position to the standing position as quickly as possible. But then we get the lamest and yet most exciting part of this entire process for me. I've loaded in a scene and I've moved the robot, all with Python, and this is actually huge. Now I'd like to do some basic R&D to determine movement information along with at what speed should we attempt to move these joints. In order to do this, it'd be really inconvenient to start and restart the sim every single time. I've been cutting out the loading times in the video, but it's more than a minute each time, and it's going to be best if we can just leave the sim up and running. For this, I've made a new script called manual control. Inside, I've just got some simple code that creates a vector of values and then saves those values to a NumPy file. This vector is just ordered in the same order of joints in the URDF, and the values will be used for the joint position in the bittleart.py file's main loop. So I'll run the manual script just once so it will actually create a position vector file, and then I'll head over to the bittleart file. First, I'll set that second loop to be a while true loop instead of ending after some arbitrary frame count. Then, what I want to do is actually load in the position vector. But we'll go ahead and do this in a try and except, since it's totally possible that we'll try to read from this file while it's being written, and we'll hit some sort of error. Then I'll move the actual update outside of this try and except. Next, I want to iterate through every joint and set that joint's position. For this, I'll create a list that is the text name for that joint, since that's how we're going to actually find it in the Omni package here. And we'll make this list in the exact same order as the position vector's values. I'll then iterate over the zipped joints and position vector, and we'll find the articulation off by the joint's name, J, and then the position target will be that position from the file. Running that while waiting for things to start, I've realized I've not imported NumPy yet, and I'm going to need to do that. So I'll just import NumPy and then try to stop the loading here. Then I go ahead and rerun, and of course I never actually saved after importing NumPy. Awesome. Saving and running again, things look so far so good. Let's try actually adjusting something. And finally, it's working. So now what I want to do is hunt for some settings for just a regular standing position, for example. It seems to me that Omniverse and Isaac Sim have a ton of features that I don't even know about, and a lot of stuff is open and kind of just up to you to figure out how to best do it. So I'm sure there are better ways to control the robot than what I'm doing here, but I'm very happy with this, and now I think it's time to at least attempt to produce a jump. In order to do that, we really just need to know the target positions for all of the legs, and then just tell Bittle to go to those positions. Later, there will likely be way more complex moves and very specific motions that we want to do, but I think this is like a good start to just kind of test this dynamic here. Another thing we need to think about is how fast do we want to go to some position, and how to stop ourselves from flying around unintentionally. This is true both in the sim and in reality. In the sim, we can probably have more force than would ever be even possible via these servo motors. But even in real life, if you move too quickly, you could fall over, and so on. So I'll start by creating a new file called jump.py to try to solve this. To begin, I think the way to do this is to just have a starting vector wherever we are, and then we have a target vector where we want to be. Then we'll have a variable to determine how fast we can actually get there, which will just be an increment per step in this case. Again, I'm sure there's better ways to do this. This is just what I've thought of for now. So then I'll iterate through the current position and target positions per each unit in the position vectors. I'll calculate the difference between these. Then I'm going to want to modify the position vector, which will later feed to the simulator as I iterate over the current position vector. So I'll make a deep copy of the current vector. I'll also be using the index value of the positions to make edits, so I'll add in an enumerate around the zip and make cpos and tpos a tuple. I wasn't actually sure the syntax was going to be valid. I don't think I've ever done that before, so I tested it to confirm and it still worked. That's pretty cool. If the absolute value of the difference is greater than the increment, then we want this position to move only by the sign of the increment and not the full amount. Otherwise, if it's not too large, then we can move by the full target difference. Let's loop through this 5 times to start, and don't forget to save to the new vector at the end and load the current vector every time. Using this for control might very well turn out to be too sloppy, slow, and unreliably timed for an actual robot or even the simulated one for control. And I acknowledge that this method of communicating with the simulator live will probably need to change later, but communicating with the simulator live is almost certainly going to be required like this. But for now, let's just try to solve one thing at a time, and right now this seems to be working okay. Running this, it does appear to be working as expected. Let's view the sim at the same time. And yeah, looking good there. We'll add a sleep and then also reset to our original starting position. And now I'll make the iteration range a bit larger, then change the target vector a bit to see it in action. It's a little jittery, but it's working pretty well. I think the jitteriness is probably actually the fault of the reading and writing of this NumPy file as mentioned earlier, because I think it would otherwise be at least a smooth motion. But that's just a guess. Tinkering with different increment speeds also appears to be working as expected. So then I develop some preset vector positions like stand, crouch, tall, and so on. Then I'll make a move function which takes a target vector and increment as parameters. Now, to jump, we can just simply crouch and then stand tall very fast. And, well, that sort of worked. The nice thing about a simulator is no parts were damaged here. While the bot is upside down, I take advantage and try to come up with a superior position so we don't flip this time. Note that I'm pretty sure we can also bind key presses to trigger certain events, so we could probably bind something to do a reset, or even a reset with a fixed base. So if we wanted to dev positions like this, we could do that probably pretty easily. I just don't know exactly how to do that yet. As I prepare some new positions, I have to reset the simulator to test them, and somewhat comically, on load, I can't help but notice that Bittle jumps pretty well here. This is happening because the stage loads in as a preset kneel, since that's how the URDF is, and then it is immediately reading that position file, which is asking for a stand, so Bittle goes as fast as possible to the new position, and this causes the jump. I still want to test the new positions that I came up with, and at least this time it doesn't flip, but ironically enough, the accidental jump is actually better than what I've just come up with. So I know that the accidental jump started off with all joints at 0, which is this sort of kneeling position, so I'll go ahead and just set up a vector with those values. I test this, just the kneel, to make sure that it works, and that looks good to me. So then I add in a move to the tall position at a fast pace, essentially as fast as possible, And look at that, it worked. Let's try that one more time. Beautiful. And with that, I think we're at a good pausing point. The next objective for me is going to be to walk or do some other complex method. But I don't want to do this manually. I want to use machine learning to at least walk or do something else in the simulator. And if I can figure that out, then I want to attempt to use the same machine learning model in the actual Bittle robot. To do this, we have quite a few hurdles to overcome, but I have a few ideas on how I want to do that, and we'll see how that goes. I'm sure it'll be super smooth. If you are interested in machine learning and specifically deep learning, then check out the Neural Networks from Scratch book by myself and Daniel Kukiewa. There, we break down all of the concepts of dense neural networks into massive detail, writing essentially an entire deep learning framework from scratch in Python, so as to get an understanding of how neural networks actually work. If you're looking to understand things with deep learning past just simply calling functions, this is definitely a book for you. You can buy the ebook, softcover, or hardcover book at nnfs.io, and the softcover and hardcover come with the ebook version. Thanks for watching, everyone, and I'll see you in another video.